Hey there, hello. In our last video, we looked at a few different operations that we can perform on matrices. In particular, we looked at some matrix multiplication and we saw that there was some strangeness involved with it. So we're going to put a pin in the properties of matrix multiplication for a moment. And instead, we're going to look at, well, what are some places where it does some pretty cool stuff? So for our beginning note here, note 7, we're going to do a little bit of an experiment. We're going to play a little bit. So let's play along with me here. I'm going to start out by taking let's go with an m by n matrix. And I'm going to represent this in general. So we have A11, A12, up to A1n. And then we have A21, A22, up to A2n, and so on and so forth, until we have AM1, AM2, up to AMN. So this is a beastly matrix, and we're going to multiply it by a less beastly matrix. We're going to multiply it by a column vector, or column matrix. And for lack of a better letter at the moment, I'm going to use X. You can use B if you want, but I'm going to use X because why not? So you have X1, X2, all the way down to X what? So as you'll recall, in order to multiply matrices, they have to have compatible dimensions. So if this matrix is m by n, and this matrix is something by 1, right, just one column, must be that in order to multiply, we have to have an n here. So this is going to be x sub n. All right, so let's see what happens when we multiply these. So as a reminder, when we multiply matrices, we're going to go across a row and down a column. So the nice part about this is we only have one column. So in the end, we're going to get an m by 1 matrix. So we're going to get a column matrix in the end here. That's pretty nice, yeah? So I'm going to take this first entry here and multiply it by x1. And then I'm going to go across the first row. So now I have A12, and I'm going to multiply that by x2, all the way over to A1n times xn. So this is going to give me A11 x1 plus A12 x2 plus la 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 A1n xn. And then we're going to have a similar thing happening with each of the next rows. So we have A21 x1 plus A22 x2 all the way down to A2n xn. And we're just going to continue finding these gorgeous sums here. So we have a m1 times x1 plus a m2 times x2 all the way down to a mn times xn. Now, if we wanted to, we could say that this is going to equal an m by 1 matrix. So let's say this is equal to B1, B2, all the way down to B sub m. And there's nothing saying we can't represent it this way, right? So we can. Do you see why I might want to? So I'm going to do a bit of erasing here. So I did this multiplication, and notice that if we have two matrices that are equal, their coordinates have to be equal. So this first coordinate, oh, I didn't mean to erase it there. This first coordinate has to equal this first value. The second coordinate has to equal the second value, and so on. So I could think of it where this first coordinate is equal to B1, the second coordinate is equal to B2, all the way down. So this final coordinate is equal to that coordinate there. And would you say that looks familiar? Sounds like something we've done before in the past? Like a system, perhaps of linear equations? Yeah. So what note 7 is implying here is indicating is that we can take any system of linear equations and write it in terms of matrix multiplication. Now, this may not seem like a big deal to you, but it actually is, because what it means is that anything we did before with our Gauss-Jordan elimination or Gaussian elimination, anything that we were doing before to solve a system of linear equations, we are going to be able to interpret it in terms of matrix multiplication. So if we find a way to solve an equation with matrix multiplication that's easier or nicer than Gauss-Jordan elimination or Gaussian elimination, that will give us a quicker way to solve systems of linear equations. So that's kind of where we are heading. And the way that this will typically be written, this is our coefficient matrix A times the variable matrix X is equal to the matrix B. So we can write any system of linear equations as a product of matrices. So because we can do that, let's do an example of that interpretation. And then let's see an example of how row reduction is going to correspond to this matrix multiplication. Alrighty, for this example, we are going to represent this system of equations using matrix multiplication. So here's how we achieve that. First, we're going to find our coefficient matrix. So I'm just going to pull all of these coefficients here. And form my matrix that way. So this is going to have a 2 by 3 matrix, 2, 4, -3, -6, 5, and 8. Now, this system had 3 variables, x1, x2, and x3. So that's going to form my column matrix for the x. And then, be careful because you don't want to get stung. Here's the b's. So we're going to get 0, 1. And that's it. That's all we have to do for this problem. Just basically translate from one form to another. So algebra is all about finding these parallel realms. So what we're doing here is we're taking the realm of systems of linear equations and now transporting ourselves to this parallel realm of matrix multiplication. So if we are indeed in a parallel realm, then our row operations ought to correspond to something involving some matrix multiplication. So let's examine that and do an example so we can see it happening. So what this note is saying is that elementary row operations can be written as a multiplication of elementary matrices from the left. So there's a reason that our elementary row operations and our elementary matrices had the same terminology. And that's because all along they were secretly connected and we didn't even know. I mean, we probably knew something was up, right? Because an elementary matrix is if you take the identity and you perform one row operation on it, that's an elementary matrix. So in just the definition of what an elementary matrix is, we already know that there's going to be some, connection to elementary row operations. So here I have an example of a matrix that I took that I used row reduction on to get to the identity matrix. Now, this is going to be basically what we're striving to do for a lot of our work with row reduction and with matrices. Because, for instance, if I had an augmented column here, right, this would mean that x equals this, y equals that, and z equals this other thing. So ultimately, our goal, if we are in reduced row echelon form, is to get an identity matrix. If we're square, right? If we're not square, we can't get an identity, but we can try and get something identity-ish. So these were our row operations that were performed. And we're going to write this in terms of matrix multiplication and then check it to see if it works out. So to begin with, I'm going to start with this first matrix that we started with. And I'm going to write it all the way over here for a reason. So I'm going to write it over here for now. So we have 1, 0, 0, 0, 0, 1, 0, 2, 0. Next, I'm going to look at that first row operation that was performed, this 1/2 row 3. And I'm going to think if I have the identity matrix, which I have here so I can visualize it easily, if I were to do half of row 3, the first 2 rows would be the same, and this would become a half. So the elementary matrix corresponding to this row operation is going to be, well, let me just write it here, 1, 0, 0, 0, 1, 0, 0, 0, a half. So this row operation corresponds to this matrix. Now, I was going to write it here, but I didn't have a whole lot of space. And the reason I wrote it to the left of my beginning matrix is because that's what this note says. It says we have to multiply by the elementary matrix to the left. So we're used to writing stuff on the right. So we're going backwards here, friends. We're going to the left. So next, we have a row operation where we switch rows 2 and row 3. So we have to find the elementary matrix corresponding to that. Now we're finding an elementary matrix, which means you always start with the identity. The rest of this is gone out of our heads. So think of beginning with the identity matrix and what happens when you switch rows 2 and 3. Well, row 1 will stay the same. Row 2 is now going to be on the bottom, and row 3 will now be in the middle. So this is how we can write this row reduction, or these elementary row operations, in terms of multiplication of matrices. Okay, so let's check to see if this actually works, right? Now, we haven't proven any properties of, matrix multiplication yet. So we don't know if this is associative. So we're going to have to go from left to right, like you do when all other things are, considered equal. So let's multiply these two matrices. So we're going to get 1, 0, 0, which is a 1. Then we have 0, 0, 0, 0, 0, 0. So here we have a 0, 0, 0, 0, 0, 0, 0, 0, a half. And then we have 0, 0, 0, 0, 1, 0, 0, 0, 0. Most excellent. And now we can multiply these two matrices together. So I'm going to work through that quickly. You can work through it quickly if you want, and then we can compare answers, okay? All right, so it looks like when I did this multiplication, I ended up getting the 3 by 3 identity matrix, which is where we ended up after we did our row operations. So this is looking good. It's sort of supporting what this note was saying. Moreover, you can kind of see what the note is saying happening here when we multiply to these two matrices here. If I think about this as my first matrix starting, and then I think about this as the elementary matrix, I'm multiplying the blue one by. This one is the elementary matrix corresponding to switching the first and second row, or sorry, the second and third rows. So if I take this matrix and I switch the second and third rows, I end up with this one here. It's like a magic trick, right? So this note is being supported, and we'll need this perhaps, in the future when we are maybe writing a proof or something. Who knows? Who can say, really? So that's it for this video. We just wanted to see some connections between systems of linear equations, and matrix multiplication. In our next video, we're going to introduce some terminology. We're not going to dig, too deep into it, but we are going to introduce what an eigenvalue and an eigenvector are, because those are also a little related to multiplication of matrices. And so we're just going to define them, see what they are, and then move on. They will make an appearance later on. So yeah, hope you found this video helpful, and see you in the next one. Bye.